These two events appear to have nothing in common: the violent collapse of a human airway on the left and the delivery of life-saving oxygen through a green mask on the right. Yet they are driven by the exact same physical principle. If you blow air into a flexible tube, logic suggests the outward pressure should force the walls open. But in this cross-section of an airway during sleep apnea, the opposite occurs. As air accelerates through the narrowed space, it creates a drop in pressure that pulls the soft tissues of the throat inward. This makes the airway's diameter a variable that clinicians have to manage. As the faster the air moves, the more the surrounding anatomy works against it. Because the human body is a network of branching, tapering tubes, it is constantly subjected to these fluid flow dynamics. For example, when a mucus plug obstructs a branch of the tracheobronchial tree, it forces air through a tighter gap, creating a pressure drop that causes an uneven distribution of gas to the lungs. This isn't limited to the lungs. Plaques in the vascular tree create the same effect with blood flow, potentially diverting it away from the areas that need it most. These are the mechanical rules of the body, and they operate identically whether the fluid is air or blood. To understand why these systems fail, we have to look at the relationship between velocity and pressure. When a fluid passes through a restricted diameter, it must change its behavior to keep energy constant. This diagram of a narrowed pipe shows that as the diameter shrinks, the fluid must speed up to move the same volume through the smaller gap. This acceleration results in Bernoulli's principle. As the velocity of the gas increases, its pressure radically drops. If we create an opening at this exact low-pressure pinch point, the drop in pressure becomes so significant that it sucks outside air directly into the main stream. Any apparatus that combines a tube, a constriction, and an opening like this is known as a Venturi apparatus. In this specific configuration, the high speed of the gas creates a powerful suction, effectively transforming the pipe into a pump. This explains why the airway collapsed in our earlier example. The high-speed air moving through the obstruction lowered the internal pressure until the airway walls were drawn together by the resulting vacuum. This becomes even more complex at a bifurcation. Due to the Coanda effect, this high-velocity, low-pressure flow tends to stick to one side of the branch, causing air or blood to be distributed unevenly. This is the mechanism behind coronary steal, where blood flow is pulled into one vessel at the expense of another because of the pressure dynamics at the junction. While these fluid physics can severely compromise human anatomy, they are highly predictable, making them reliable enough to be repurposed for medical treatment. In clinical practice, this vacuum effect is used as a precision tool. By controlling the diameter of the constriction, clinicians can precisely control gas mixtures. This diagram shows 100% oxygen entering a Venturi mask nozzle and shooting through a narrow orifice. The pressure drop draws room air through side ports, diluting the pure oxygen to a calibrated value, in this case 24%. By changing the size of the nozzle aperture, such as switching to a green mask, clinicians can change the ratio of room air that is drawn in, delivering exactly 60% oxygen. Because the oxygen concentration is dictated by the physical geometry of the nozzle, the mask provides a reliable gas mixture without the need for electronic monitoring or moving parts. This same Bernoulli vacuum is used in nebulizers, where fast-moving oxygen sucks liquid medication from a reservoir and breaks it into an inhalable mist. It is also the basis for jet ventilation, where high-speed oxygen delivered through a small catheter in the trachea and trains the surrounding air to ventilate the patient. In cases of laryngospasm, clinicians may even use helium. Because helium has a low density, it reduces the velocity and turbulence of the gas flow, which helps relieve the obstruction in the larynx. From the collapse of an obstructed airway to the precision of an oxygen mask, the Venturi principle is the physical foundation for both the clinical challenges and the tools used to overcome them.